Alright, so hello and welcome everyone. This is week 9 of interactive sessions for the course Computational Fluid Dynamics for Incompressible Flows. As you all know, this course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I am a PhD scholar at IIT Madras, and like every other week, we will be solving some problems together. So let's jump into question number 1. So this week our main focus has been on the marker and cell method and using uh, the technique to solve Navier-Stokes equations, unsteady 2D Navier-Stokes equations in particular. So there are some things called the collocated grid and the staggered grid which we learned about. So this question is regarding that. It's asking what is the primary difference between a staggered grid and a collocated grid. Is it option A, the location of the grid points relative to the fluid flow? Is it option B, the resolution of the grid in different regions of the computational domain? Is it option C, the type of interpolation used to calculate the values of fluid variables? Or is it option D, the number of dimensions used to represent the computational domain? Where are these two types of grids mainly different? So read the question carefully, and once you have figured out the solution, you can either type in the chat box or you can unmute and answer as well. So the types of the grids are hidden in their names itself. So co-located, meaning located in the same place, and staggered, meaning some things are staggered, they are not overlapping on each other. Okay, so we have two responses, one in favor of option A, the other one in favor of option C. Let's have a look at the solution. It's actually, okay, the colors are reversed. Sorry about that. So the red one is the correct one and the green ones are wrong over here. So the location of the grid points relative to the fluid flow. What happens is in a co-located grid, let's say if this is our computational domain, and let's say we divide it into 9 grid cells like this, then we will store all the values of, let's say, the pressure, the velocities, and everything we will store in the cell centers only. This is what a co-located grid looks like. Co-located. So all are located in the same place. Whereas in a staggered grid, the values are stored in a staggered manner. So what is usually done is something like this. So let's say if this is the grid for the pressure, so at the cell centers, the pressure would be stored and the velocities are stored in a staggered manner. So at this face center, U will be stored. So one U will be here, one U will be stored here, another U will be stored here, like this. At all the uh, vertical faces, U will be stored and the y direction velocity. So let's say this is x, this is y. So and the v velocities, the y component of the velocities, they will be stored in the cell faces like this. So you see these have a different, uh, what can I say, cell boundary which looks like this. So they are stored in a staggered manner, not overlapping on each other. So that's the main difference on where the grid points are located relative to the fluid flow. Okay, any questions on this? All right, so if there are no questions, we'll move on. We'll move along to question number 2, which is asking us what are the number of cells for U and V respectively. So we saw how U and V are stored in staggered grid. So this is with regards to staggered grids. Respectively, if P has M cross N cells, is it option A, M cross N for both U and V? Is it M plus 1 cross N for U and M cross N plus 1 for V? Is it M cross N plus 1 for U and M plus 1 cross N for V? Or is it M plus 1 cross N plus 1 for both U and V? So here M are the number of rows and N are the number of columns. So let's say if I draw something like this. So here I have two rows. So M is equal to 2 and N is equal to 4. No, sorry. So M is the number of columns and N is the number of rows. So in this case, M is equal to 4 and N is equal to 2. Okay, so we have one response in favor of option D. That is, both would have N plus 1 cross N plus 1. Let's see what others have to say. You can consider this grid itself for visualization. How many grid points of U would be required and how many grid points of V would be required if I staggered this. Let's use a different color of ink for this. How many U's would be there? One U would be here, 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 and here. Similarly, this would be repeated here as well in the second row. Right. So, how many values of U are there? It's 5 cross 2, right? So, in this case, if M was 4 and N was 2, then this is M plus 1 cross N. Then let's look at what would happen to V. So V1V would be here, another here, and another here. And same thing repeated all over. So how many values of V has to be stored? It would be 4 cross 3. So if M is 4 and 2, N is 2, then it's M cross N plus 1. So this actually corresponds to option B. Let's have a look at the solution. It is option B. So I hope the explanation is clear, right? Please ask if you have any doubts. So the number of columns would increase for U and the number of rows would increase for V. Okay. All right. So if there are no questions, we'll move along. We'll move on to question number 3 now, which is again regarding staggered grids. So it's asking us to match the following. So on the left-hand column, we have different variables U, V, and pressure P. And on the right-hand column, we have different locations where these values are stored. So we have number 1 cell centers, number 2 vertical faces, number 3 horizontal faces, and we have to match them. And there are multiple combinations given in the options below. Once you have correctly matched all of them and found your combination, you can select them from the 4 options. So what I mean by these is that, so this is the cell center. The vertical faces are these ones on the left and the right. So this is 2, this is also 2. And the horizontal faces are this one, these ones. Let's see, we have one quick response in favor of option C, that is A2, B3, C1. So A2, B3, C1. That looks correct. Let's have a look at the solution. It is indeed vertical faces. Yeah, actually option C is correct. It shouldn't be option D. So this is what I mean by a horizontal face. And that's where V is stored, right? So V should be 3 and A should be 2 and P should be cell center. Yeah, correct. So C is correct. Okay. Now let's move on to question number 4. This is asking us which of the following is a limitation or a disadvantage of staggered grids. Is it option A, that it is only suitable for incompressible flow simulations? Is it option B, that it can only be used for two-dimensional flow simulations? So the main points are incompressible, 2D. It is less accurate than other numerical methods. Or is it option D, it requires difficult bookkeeping? What is the disadvantage of using staggered grids? Okay, so we have one response in favor of option D. Let's hear what others have to say. There's no hurry. Read the question carefully and figure out the correct solution to it. Then you can type it in the chat box. Okay, so let's have a look at the solution. It is indeed option D. The bookkeeping, the maintenance of the data in different organized data structures, that becomes very difficult, because we already saw that the dimensions of these variables are all different. So if P is a m cross n matrix, U would be m plus 1 cross n, and V would be m cross n plus 1. And on top of that, let's say instead of so if we had used a uniform grid, then so I'm just using a simple one here. So if let's say this is P, then I'll have a U grid cell like this, or let's make it 3 by 3. So this bold lined cell, this is where all the scalars are stored, right? Then for the U cells, so I'll use a different color again. So all the U grid cells are these ones, these red ones, right? And for the uh, V velocities, these grid cells are used. Now you can imagine that if this is uniformly spaced, well, sorry, this would be delta y. I'm just showing with for the y now, and this distance, this is called delta y, like this. So for a uniform grid, all these values of delta x, delta y, delta x, delta y, these are uniform. Imagine if we use a non-uniform grid now. So we'll have to maintain all these data into, again, matrices of different sizes, right? Multiple matrices, 4 more matrices, which has to be stored always, and they will be used in the calculations as well. It becomes a mess. You can imagine that, right? So that's why the bookkeeping becomes very difficult. Writing codes and maintaining the data, that becomes extremely crucial. For uniform grid itself is difficult because of the uh, different sizes of these matrices. On top of that, for non-uniform grid, there will be additional problems, because then these delta x, delta y, these don't remain fixed constants. They or single numbers. They would be a matrix of multiple numbers. I hope I could make my point clear. Any questions from you guys? All right. So if things are clear, we'll move on to question number 5 now, which is now asking for a limitation of the collocated grid, not the staggered grid. So we discussed about the staggered grid earlier. Now, what is the disadvantage of the collocated grid? Is it option A, only suitable for incompressible flow? It is less accurate due to the use of a coarser mesh than the one considered. Is it option C, that it produces spurious results in case of checkerboard velocity or pressure fields? Or is it option D, both B and C? Which one is true? So we have a response in favor of option C. Let's hear what others have to say. Read all the options very carefully. So we have the 5th question of today's session here. It's asking us which of the following is a limitation of the collocated grid. Is it option A, that it is only suitable for incompressible flow simulations? Is it option B, that it is less accurate due to the use of a coarser mesh than the one considered? Is it option C, that it produces spurious results in case of checkerboard velocity or pressure fields? Or is it option D, both B and C? Someone has responded that it should be option C. Let's hear what others have to say. Okay, so option C gains more support. Let's have a look at the solution. It's actually option B, both B and C. So since you guys already responded with option C, I guess this makes sense, because we know that for checkerboard velocity or pressure fields, they get decoupled, and the results are not correct if we use a collocated grid. On top of that, let's say this is a very special case, right? When the checkerboard pressure or velocity field is given as an input in the first place. Even if that is not there, then also what happens in reality is that we end up using a coarser mesh effectively than the one which we take initially. So let's say if this is our starting grid with a grid spacing of delta x, this is PP, this is PE, the east one, then PW, the west one. And we see that, in case of finding out dopey dou x, we at the point P. So here, and this is small e and small w, let's say. These are the cell faces. So we have to use P small e minus P small w divided by delta x. That should be dopey dou x. But in collocated grids, at the cell faces, pressures are not stored. They are stored only at the center. So we have to find them somehow by interpolation. So how do we find the one at PE? We take an average of that between PP and P capital E. And if we make those substitutions, then it ends up being P capital E minus PW divided by 2 delta x. So this 2 delta x means that we are using a coarser mesh of spacing 2 delta x rather than delta x, which we had already started with. So effectively, the mesh which we are using, that becomes a uh, 2 times bigger mesh. So that also reduces the accuracy of our solutions. So option B is also a disadvantage of using a collocated grid. That's why the correct answer to this would be option D, that is both B and C. I hope that makes sense. Any questions on this? Okay, so if there are no questions, we'll move on. We'll move along to question number 6 now. So the staggered grid can be used to overcome what? Is it option A, the decoupling of pressure and velocities? Option B, coupling of pressure and velocities? Option C, interpolation problems? Or is it option D, boundedness problems? Okay, so very quick responses in favor of option A. So this is a direct consequence of the problems faced by the collocated grid, where the pressure and velocity gets decoupled. That problem is overcome in staggered grid. So what happens is, if we look closely, uh, so I'll just use 2 grid cells for this. So here is one P, let's say this is PP, and here is another pressure, let's say P capital E, and here UP is stored. So during the solution of UP, it happens so that there is a, so just focus on this grid cell now, where U is stored, the velocity U. So here I have a pressure, here I have a pressure, and it's as if within this control volume, the pressure difference just across the 2 faces, that is driving the flow inside. So this makes much intuitive sense, right? So there is a control volume, there are 2 different pressures on 2 faces of it, and that is what is driving the flow. Right. So if there is a pressure difference, so let's say if PP is greater than PE, so it makes sense that it will there will be an effective force acting on this fluid element towards right. So that's what drives this flow, and all that this attains is actually the coupling of the pressures and the velocities. And this is the main reason why staggered grids work so well. They are used to overcome decoupling of pressure and velocities, what happens in collocated grids and results in those uh, checkerboard patterns. So was this clear, this idea? Okay. All right, so we'll move along. We'll move on to question number 7 now. We're moving really quickly today. So anyway, so which of these is not stored at the cell centers in the case of staggered grids? Is it option A, density? Is it option B, pressure? Is it option C, temperature? Or is it option D, none of the above? Read the question carefully and then pick out your answer from the options. Okay, we have one response in favor of option A, density. Let's see what others have to say. Which of these is not stored at the cell centers in staggered grids? Okay, option A again. Anyone else? Any other answer? So where is it that density is stored, if not in the cell center? You can unmute and answer if you feel comfortable. Otherwise, you can type in the chat box as well. Where is density stored? Okay, forget all that. Tell me, is density a scalar or a vector? Which one is it? A scalar, right? And in case of staggered grids, all scalars are stored at the cell center. At the cell faces, only the velocities are stored. So it should be option D, none of the above, because density, pressure, temperature, these are all scalars. Okay, so the correct answer should be option D over here. Does that make sense? Huh? So not only these three, other scalars also. So let's say in case of combustion simulations, their chemical reactions go on. So there is not just the mass of the mixture, the mass of individual uh, compounds and elements, they have to be, or compounds and elements also known as species. The chemical species also have to be conserved. So that is also a scalar value which is stored. In case of multi-phase simulations, there is something known as a Eulerian method, where the continuous phase as well as the dispersed phase are treated as two Eulerian fluids intermixed with each other. In that case also, the concentration of the dispersed phase, that also is a scalar, and in case of staggered grids, those quantities are also stored in the cell centers, just like pressure, temperature, density, and all that. So the thing is, all scalars are stored in cell centers. Okay. All right. So I hope this is clear. Let's move along. We move on to question number 8 now, which is asking us to calculate drag or lift. Which method is more suitable? Is it option A, stream function vorticity approach, something we learned last week, the stream function vorticity approach, or is it the primitive variable approach? Primitive variable means all the primitive or the well-known, well-used uh, quantities which define the state of a fluid, state of a flowing fluid, U, V, and P formulation. So this is known as a primitive variable formulation, and this is known as a derived variable formulation. because you can see that psi and omega, these are derived from velocities, right? So we have a response in favor of option B, primitive variable approach. Let's see what others have to say. So let's say I have a cricket ball like this, which is moving with a velocity u in this direction, or uh, in quiet air. And the way to think of this problem is we can, use a D'Alembert's principle and say that no, this ball is fixed, stationary, and there is a flow around it, which is coming at a velocity u. Right? So draw this properly. So if there was a uniform flow coming like this, and there will be, of course, streamline patterns forming like this, which I'm sure you have seen multiple times. Right? And this flow would exert some forces on the ball, and the way they are defined is if it acts against or acts along the direction of the flow, then that force is called drag, and if it acts perpendicular to the relative velocity between the solid object and the fluid and the flowing fluid, or the direction of the flow, then that is called a lift force, FL. How are these calculated? Or if they are, if they have to be calculated, then which method is more suitable? So all of you, okay, so someone has said it's a stream function vorticity approach. So first tell me this, someone has to tell. So FL and FD, how they are calculated? What should our approach be? Forget CFD. In general, how are these calculated in basic fluid mechanics? Yeah,
Sir, is it the frontal area of the object we have to take care, the density, velocities,
yes.
values?
So these two are okay. The density and the frontal area we have to consider. Then there will be a CL and then the velocity squared. You are right there. But this value of CL is unknown in the first place. If I have to calculate that, we need to compute this in a different way. And the way it is done is that, so if this is the solid object, there is a pressure at different points acting due to the fluid. Okay, there is a pressure along different walls of it, and so this entire pressure, and this is inviscid fluid flow theory. There is no consideration of viscosity as of yet. Okay, so there what is done is that this P at each point will have two components, right? So let's say I'll blow this region up. So I'm zooming in over here. So there is this part. There is a pressure acting on it, normal to the surface. So this can now be resolved into two components, right? One in the y direction, one in the x direction. And if this angle is theta, so I'll move this P here. This is P. So if this angle is theta, then the force in the x direction would be P cos theta, and this would be P sin theta, right? So what is done is that, so along this entire surface area, the integral of the horizontal force and the vertical forces are taken to find these. So for FL, it will be the vertical force. So it would be P sine theta r d theta, theta going from 0 to 2 pi. And mind you, P here is a function of r, not a constant. Similarly, for drag force, it would be 0 to 2 pi p cos theta r d theta. So the main thing which we require is basically p at different points of r as a function of r, or not r, theta. R is constant, r is equal to capital R, the radius of the ball, and at different values of theta, the values of p are different due to the fluid flow. If we know that, then we can calculate the lift and drag. And for that, the primitive variable approach makes more sense because p is something that we are calculating in the first place. Using stream function vorticity approach also we can do that, but for that we need to separately solve the pressure Poisson equation which we saw earlier, if you remember. This can also be done, it's not that can't be done, but the primitive variable approach is more suitable because p is itself being calculated during the process. So the correct answer would be option B. Does that make sense? Any questions, anyone? So the thing is, in multiple cases, these integrals are actually calculated, and that gives us the values of these CL and CDCL values. You will find many handbooks, engineering handbooks, as well as there are online toolboxes as well, where if you input different flow conditions and geometries of solid objects and so on, if you give all the inputs, it will throw out some CDCL value, and that's what is very important, because then if we know the CDCL for a certain condition, then we can simply find out the lift force by just plugging in the rho a v square data only. V square by 2 is used actually. So v square is the relative velocity between the object, the solid object, and the flow. So if we simply plug in these simple values and obtain the CL value from some table or chart or some online toolbox, then we can directly find out the force acting on the objects. These ideas are very important in case of aircraft design, as well as many things. Aircraft design is something that comes off my mind. Then the sports ball dynamics, in that case is also CLCD becomes important. In case of modeling sprays, what happens in sprays is that there are a bunch of droplets which are moving in air, right? So in that case also you can model the droplets as spheres which are moving in quiet air. So there also the drag force and lift force on those spheres can be found out using the exact process which we discussed here. And there are multiple other examples also. There's nothing else coming to my mind now, but these are the only ones off the bat. Okay. Any questions on this? And yeah, so for generating these CDCL databases, CFD has played an immense role in academic as well as industrial research. Yeah, please go ahead.
So there is one doubt about this: how to take surface roughness effect when we are calculating CLCD, because they
When
will affect a lot.
yeah, it will affect. So there are multiple approaches being taken. One very simple approach, the idea is simple but implementation is difficult, where the surface roughness is usually denoted by some epsilon by d, right? So let's say if I have a ball of or let's say a cylinder which is of diameter d, and it has a roughness of average epsilon all over it. Okay, so something very weird like this. So one thing you can do is you can actually make a geometry which is like this, and then do a direct numerical simulation or DNS and find out what are the effects of different values of surface roughness. So that's one way of doing things. Another way is performing experiments with taking different surface roughnesses, and there are some more advanced techniques as well where the effect of the roughness is modeled into it. So there are different models of how surface roughness might affect the boundary layers around these objects, that kind of an idea. But those are more difficult to formulate. And this, what I told, direct numerical simulation, this is the idea is simple, but performing it will take a lot of computational resources, because all these fine scales you will have to resolve. In that case, you'll have to take mesh which is very fine and can take care of all these. Does that answer your question?
Sir, like I was trying on the airfoil.
Yeah.
So in that case, I was asked to show the effect of surface roughness on the results.
Mm.
Then I was not able to answer anything because they said you should show a surface roughness when calculating CLCT.
Yeah.
Otherwise, it is of no use. So how to
So
incorporate? Like I'm
yeah,
really not
I
clear
don't
with it.
have the I don't have a direct answer to your question. I'll look into it and get back to you next class. But there must be some
Sir.
models, like let's say a smooth surface, how boundary layer develops on a smooth surface. And so forget aerofoil. So let's say I have a flat plate like this, which is smooth, and there is another equivalent flat plate like this, for which there is a, so for this the epsilon by d or epsilon by l, whatever, is 0 for the smooth case, and there is epsilon by l equal to some constant value. Okay, so uh, the boundary layer which develops on these two, they will not be the same. That's where some difference will arise. So how that development will take place, there must be some, you know uh, either analytical or some numerical approach taken to resolve this. I don't have the exact answer to your question, but I will look into it. Okay. So basically what happens is, if you are considering inviscid flow, then the roughness does not really play much of a role, because the pressure distribution would be the same nonetheless. Uh, the effect of surface roughness would only come in if you are using, if you are trying to, if you are considering the skin friction drag as well, right? And the skin friction drag, that would depend on how the boundary layer behaves and what the velocity gradients are at different locations. So this gradient, the dou u dou I, that would determine the shear shear force at the wall, or the shear stress at the wall. So it's the form of the boundary layer which will affect, and if at all the boundary layer changes with surface roughness, then only it would have an effect, and it does have an effect. We know that a smooth ball and a smooth, let's say a smooth ball and a tennis ball which has a felt on top of it, they don't behave similarly, right? So there will be a difference, but how to compute that, we'll have to see. Okay. So I'll try to find out the answer to your question, and we'll get back next week. Okay. So for now, let's move on to the next question. In MAC algorithm, how is pressure at neighboring points calculated? Is it option A, by calculated by normal interpolation? Is it calculated by weighted interpolation? Is it solved using TDMA or Thomas algorithm? Or option D, is it assumed to be 0? So I won't call this pressure, this is actually pressure correction. Okay, so we have a few quick responses in favor of option D, assumed to be 0. So have a look at the solution, it is indeed assumed to be 0. So this is one of the assumptions which works. So in MAC algorithm, uh, if I remember correctly, so there was this uh, grad of p prime which comes out to be some function of u tilde and v tilde, which are the nominal velocity fields. So instead of finding out the Laplacian of p prime, we just take p prime equal to something. So that gives you a formula of p prime as a function of u and p, and p prime at p. Here it is assumed that the neighboring points to p prime, the pe, pw, pn, ps, these are all 0. P prime, by the way. This is assumed and p prime is found, and this is repeated actually. So this is found, then finally this is checked whether the divergence of u tilde is 0 or not, the vector u tilde. If this is not 0, then we go back again here and we keep on looping like this until this condition is satisfied. When this is satisfied, then we break free from it, and then we find out the uh, u at n plus 1 equal to some u tilde plus another function of the pressure corrections. I don't remember the exact formula, but this is what it looks like. Then the pressure at the n plus 1th term is also calculated as the correction is added onto the assumed values or the previous values. So it's a part of how the algorithm works that the neighboring point pressure corrections are assumed to be 0, not pressure but pressure correction. Okay, any questions on this? So what this assumption basically does is that instead of solving an equation, we will just plug in values and have a formula for getting the numbers. This makes the calculation a bit easier. It's in no way a logical assumption, but it works. So the proof is in the pudding. Okay. All right. So now we'll move on to the last question of today's session, which is asking us that in MAC algorithm, where does the pressure correction equation originate from? Is it option A, continuity equation? Is it option B, X momentum equation? Is it option C, Y momentum equation? Or is it option D, none of the above? It originates from a different equation. Which one would it be? Where does the pressure correction equation originate from? Is it continuity equation? Option B, X momentum equation? Option C, Y momentum equation? Or is it option D, none of the above? Okay, so we have a few responses in favor of continuity equation, and it is indeed the continuity equation. So it's assumed that the velocities at un plus 1 and vn plus 1, they should satisfy the continuity equation for incompressible flow. And then since these un plus 1s are function of u tilde and pressure corrections, so those u tilde and pressure corrections are substituted here, and finally we get the form Laplacian of p prime is equal to some function of u tilde and v tilde. We must know that the un plus 1 as well as vn plus 1, these are functions of u tilde, and so these are, sorry, so these are u tilde plus some, I forgot the exact form of it, but some function of the pressure correction. Once you plug them in over here, you get this equation. That's where the original pressure correction equation originates from. So MAC algorithm is one way in which this is dealt with. In future, you will see there are other algorithms like simple, simple C, simple R, which deals with the pressure correction equation in a different way. Instead of assuming that its neighbors are zero. Any questions on this? Okay, so if there are no questions, this brings us to the end of today's session. So thank you all for joining today and participating so enthusiastically. We will meet again next week. Thank you. Thank you.